Imagine a world where coffee is a luxury item, chocolate is extinct, and your avocado toast costs $50. Climate change could make this a reality. In the simplest terms, climate change refers to the long-term shifts in temperature and typical weather patterns in a place. While the Earth's climate has always fluctuated naturally, the changes we're now seeing are happening at an unprecedented rate, driven in particular by the burning of fossil fuels like coal, oil, and natural gas, which release greenhouse gases into the atmosphere. These gases trap heat from the sun, causing the planet's temperature to rise. The consequences of this warming are far-reaching and profound. We are witnessing more frequent and intense extreme weather events like prolonged heat waves, droughts, hurricanes, and coastal flooding. That extreme weather is driving more and more frequent wildfires in places like Australia, Canada, Russia, and the western United States, and is triggering coral bleaching and die-offs in places like the Great Barrier Reef. The same warming of the oceans that's driving coral bleaching is simultaneously fueling habitat destruction. Many Arctic animals that rely on sea ice as part of their life cycle are threatened by its disappearance, and rising ocean temperatures threaten the stability of the North Atlantic Oscillation, a water cycle in the Atlantic Ocean that stabilizes temperatures in Europe. Fish stocks are migrating towards the poles in search of cooler water, with massive implications for seafood production. In 2022, for example, it was discovered that 90% of the Alaskan snow crab population had disappeared from the Bering Sea. While there were several theories offered to explain their disappearance, which likely resulted from starvation as increased competition for food from other species like Pacific cod, which had migrated into the crab's habitat in search of cooler water temperatures, the collapse nevertheless forced the cancellation of the Alaska snow crab harvest, likely for the next 4 years or more. Climate change-induced sea level rise also threatens coastal communities with tidal flooding and, in the most extreme cases, such as the low-lying island countries of the Maldives and Tuvalu, could force people to flee their country, becoming climate refugees. And if left unchecked, ongoing climate change will necessitate changes in food production. As the best growing weather moves towards the poles, rising sea levels threaten coastal growing areas, rainfall patterns change, and some crops could become more difficult or even impossible to grow. Our food system is implicated with climate change on 3 levels. Food production contributes to climate change, our food system will be impacted by climate change, and advances in food production will have to adapt to and might also help mitigate against climate change. Depending upon how we calculate it, our food system accounts for roughly 1/4 of global greenhouse gas emissions, with energy production accounting for about 1/3, and industry accounting for about 1/4 of all greenhouse gases. All other activities comprise less than 15% of total emissions. Within the food system, the main sources of greenhouse gas emissions include land use, which comprises about 24% of agriculture's greenhouse gas footprint, or about 6% of total greenhouse gas emissions. Crop production, which accounts for about 6.5% of all greenhouse gas emissions, or about 27% of agriculture's environmental footprint. Livestock and fisheries, which are responsible for about 1/3 of total food-related greenhouse gas emissions, or about 8% of global greenhouse gas emissions. And the supply chain, the food processing, packaging, transportation, and retailing, which collectively comprise about 1/5 of the food chain's environmental footprint, or about 5% of total greenhouse gas emissions. Our food system, from farm to table and beyond, is thus a major contributor to global climate change. This occurs in a variety of ways. Most contemporary agricultural practices release significant amounts of greenhouse gases. Deforestation and land use change, converting forests and natural habitats into agricultural land, releases significant amounts of carbon sequestered in trees and soil, while simultaneously reducing the Earth's capacity to absorb CO2. Livestock production, particularly ruminants like cow and sheep, produce methane during digestion. And the use of synthetic fertilizers and manure management releases nitrous oxide, another potent greenhouse gas, into the atmosphere. Meanwhile, the production of synthetic fertilizers and pesticides themselves is an energy-intensive process that involves the release of CO2 and other greenhouse gases. The production and processing of food requires substantial amounts of energy, often derived from fossil fuels. This includes the operation of machinery, irrigation systems, and processing facilities. The distance food travels from farm to table, often described using the idea of food miles, contributes to greenhouse gas emissions. And depending upon the distance traveled, the mode of transit, and the perishability of the food product, this can add up. Transportation of bulk grains via cargo ship, for example, has a comparatively small footprint when contrasted with expensive, perishable, and thus climate-controlled fish flown from fisheries on the other side of the world to be served fresh to the final consumer. Food choices thus matter. Diets high in animal protein like meat and dairy have a larger carbon footprint compared to plant-based diets. Processing animal-based foods typically requires more resources, including land, water, and feed, and results in higher greenhouse gas emissions. Finally, food waste is a major problem contributing to unnecessary greenhouse gas emissions. A significant portion of food produced globally is wasted, and as that food decomposes in landfills, it generates methane. Reducing food waste can significantly lower greenhouse gas emissions. And just as important, the production and disposal of food packaging, particularly plastics, contribute to greenhouse gas emissions. Energy is required to produce packaging materials, and improper disposal can lead to environmental pollution. Reducing excessive packaging would thus contribute to reducing greenhouse gas emissions. The cumulative effect of these processes makes the food system a significant driver of climate change. But even as our food system contributes to climate change, it is simultaneously impacted by it. Indeed, agriculture, the foundation of our food system, is highly vulnerable to the impacts of climate change, which pose significant threats to food production, livelihoods, and global food security. There are a variety of ways this might occur. First, rising global temperatures and changing precipitation patterns directly affect crop growth, yields, and agricultural productivity. Warmer temperatures can accelerate plant growth, but may reduce yields for many crops. Changes in rainfall patterns can lead to droughts in some areas and flooding in others, both of which can damage crops and reduce yields. And irregular precipitation can disrupt planting and harvesting schedules, reducing agricultural efficiency. At the most dramatic level, warmer temperatures can shift growing seasons, potentially leading to earlier flowering and harvest times, or exposing crops to late-season frosts or disrupt pollination patterns. Regions may experience shorter or longer growing seasons, and as temperatures rise, suitable growing zones for individual crops can shift, potentially making some regions less suitable for certain crops and opening new areas for cultivation. Adapting to these changes can be challenging and costly for farmers, either shifting to new crops or relocating their farms to more suitable growing regions. Climate change is increasing the frequency and intensity of extreme weather events like heat waves, droughts, floods, and storms. These events can devastate crops, leading to significant yield losses. For example, a severe drought can cause widespread crop failure, while floods can wash away or drown crops. Extreme heat can damage crops through heat stress or increased evaporation. Climate change is exacerbating water scarcity in many regions. This poses a significant challenge for agriculture, which accounts for about 70% of global freshwater use. Reduced water availability and growing competition over water from other sectors like urban areas and industry can limit water availability for irrigation and agriculture, leading to lower crop yields and potentially forcing farmers to switch to less water-intensive crops. And this impact is amplified by the acceleration of evaporation rates from soil and water bodies resulting from higher average temperatures, further reducing water availability for agriculture. Warmer temperatures and changing precipitation patterns can alter the distribution and life cycle of pests and pathogens, leading to increased crop damage and livestock diseases in areas previously unaffected. New pest species may emerge in regions where they were not historically a problem, challenging existing pest management strategies. Climate-related disruptions to agriculture can also lead to reduced food production and increased prices and price volatility in global markets. When major agricultural regions experience significant yield losses due to climate events, it can cause food prices to spike globally, affecting food security, particularly for vulnerable populations in developing countries. This can occur both as a result of reduced yields in supply disruptions caused by climate shocks, droughts, floods, and the like, or from higher overall production costs due to the expense of adapting to climate change, for example, from increased irrigation costs, greater need for pest control, and so on. And reduced crop yields and livestock productivity triggered by climate change can lead to lower overall global food availability, exacerbating food insecurity, especially in vulnerable regions. The impact of all this will be felt disproportionately around the world. Developing countries, which often have less capacity to adapt, face greater risks from climate change, exacerbating existing food insecurity and productivity challenges. That said, there are a variety of adaptation and mitigation efforts already underway in the food system, and countless other strategies are being developed. Remember that adaptation strategies emphasize adjusting agricultural practices and systems to better cope with the current and anticipated impacts of climate change, with the goal of reducing vulnerability and increasing resilience to climatic changes, ensuring the continued productivity and sustainability of agriculture. Examples include diversifying crops to reduce the risk of crop failure and increase crop resistance, improving water management to ensure the most efficient use of water resources, for example, by implementing efficient irrigation systems, rainwater harvesting, or fortifying water storage techniques. Developing climate-resistant crop varieties that are better able to tolerate more extreme growing conditions with traits like drought and stress tolerance. Adapting agroforestry practices, which enhance resilience and biodiversity by integrating trees and shrubs into the farming system to provide shade, improve soil quality, and offer additional products like fruit and timber. Improving soil management to maintain healthier and more productive soil by, for example, adopting no-till farming methods, cover cropping, and composting to improve soil organic matter and water retention, and employing precision agriculture to optimize input use and increase farm efficiency. Mitigation strategies, on the other hand, are aimed at reducing the greenhouse gas emissions themselves, seeking to limit or prevent climate change in the first place. These strategies focus on minimizing agriculture's carbon footprint, and given its comparatively large carbon footprint, there is considerable opportunity in this area. Researchers, for example, are currently developing improved feeding strategies, manure management processes, and developing new breeds through selective breeding effort with the goal of reducing methane production from livestock. Another area of research focuses on improving nitrogen use efficiency. By more precisely applying fertilizers, using nitrogen-fixing cropping, and slow-release fertilizers, researchers hope to reduce the amount of fertilizers that need to be applied, thus reducing farming costs while simultaneously reducing the problem of over-application and the excess runoff that contributes to climate change and eutrophication. Reducing food waste would also make a significant contribution in reducing agriculture's carbon footprint. This occurs through multiple avenues. First, by preventing food waste from entering landfills, we immediately reduce the release of methane from its decomposition. But more broadly, the more efficient use of food resources translates into environmental and economic savings as the chemical, labor, land, seed, and other inputs used in farming food that goes to waste themselves are wasted. Reducing or eliminating food waste would thus reduce the need for all of these. A variety of sustainable farming practices would also help mitigate greenhouse gas emissions. Practices like organic farming, conservation agriculture, and integrated pest management all reduce the chemical inputs and enhance ecosystem health, lowering farming's overall ecological footprint. There's also considerable interest in enhancing and expanding carbon sequestration in agriculture. Practices like afforestation, reforestation, and attaining healthy pastures that absorb and store carbon could dramatically reduce agriculture's greenhouse gas emission levels. At the most dramatic level, some advocates are calling for net carbon negative agriculture, a food production system that would sequester more carbon dioxide from the atmosphere than it emits, effectively reducing the overall concentration of greenhouse gases. Achieving net carbon negative status in agriculture would necessarily involve a combination of practices and technologies that enhance carbon sequestration, reduce emissions, and improve overall sustainability. There are several real-world examples of farms that have achieved this goal. Brown's Ranch in North Dakota is a pioneer of regenerative agriculture and has transformed his degraded farm into a thriving ecosystem. By implementing practices like no-till farming, cover cropping, and diverse crop rotations, he has increased soil organic matter, improved water retention, and boosted biodiversity. His farm is estimated to sequester several tons of carbon per acre each year. White Oaks Pasture in Georgia is a diversified livestock farm that has adopted regenerative grazing practices involving rotating cattle across pastures to mimic natural herd behavior. This approach helps improve soil health, increases carbon sequestration, and reduces reliance on synthetic fertilizers and pesticides. The farm also uses renewable energy resources and composting to further reduce its carbon footprint. A 2021 study found that White Oak Pastures sequesters more than 3 kilograms of carbon dioxide equivalent per every kilogram of beef produced, making it carbon negative. Soulfire Farm is an Afro-Indigenous community farm in New York, practicing agroforestry, integrating trees with crops to improve soil health and sequester carbon. It also uses cover cropping and no-till farming, and incorporates biochar to improve fertility and sequester carbon. It emphasizes regenerative agricultural practices that enhance soil health, increase biodiversity, and sequester carbon, contributing to a net negative carbon footprint. There are lots of others, but the point of these examples is to illustrate that it's possible to rethink agriculture and envision, and more importantly implement, a sustainable system. But that's it for now. Please leave any questions you have in the comments section below, and thanks for watching.